Hello and welcome to Mathematics with Simon. I'm Simon and this is Chewy. And this is some honey roasted ham, which Chewy will get at the end if we successfully navigate this interesting subject. My friend Bill got in touch with an interesting mathematics problem, and I thought it was a great thing to look at and also to think about what it's like to be a mathematician. So the problem is this: consider a combination lock, like the sort of lock you might have on a bicycle, with 4 tumblers. Each tumbler contains the numbers from 0 to 9. And the question is, how many different codes can we make that add up to 8? So this video is all about what it's like to be a mathematician. Now, anyone can be a mathematician, whether you're at school, whether you're doing your A-levels, or you're 10 years old, or you're at university. We can all be mathematicians. It's just really a state of mind. It's about sort of finding interesting and fun solutions to mathematical problems, and it's about never giving up. So let's start with some basics. The number of possible codes is 10 times 10 times 10 times 10. There's sort of 10 options for the first tumbler, 10 for the next, 10 for the next, and so on. So there's 10,000 options. They can add up to anything between 0 and 36. So if all the numbers are 0, it adds to 0. If all the numbers are 9, it adds to 36. That's the maximum. There's only one way to get each of these, but if we want to have a code that's adding up to something in between, there's a lot more ways. So to get 18, we could do 4545 or 5454 or 9900. There's loads of ways of getting the ones in the middle, we observe. So I started off by just asking what numbers are in the code. So you could make it up with 0008, 0017, 0026, 0035. I just listed all the possibilities. Then I thought about, for each set of numbers, how many ways there are to permute it, how many different orders you could put them in. So there are 4 orders for 0008. There are 12 for 0017, because there's 4 ways of placing the 1, and then there's 3 ways of placing the 7, so that makes 12, and then the noughts look after themselves. There are 6 ways for 0044, because there are 4 ways for the first 4, 3 ways for the second 4, then you have to divide by 2 to eliminate double counting. There's only one way to place 2222, because it's just 2222. So what I then did was add up all the permutations of all the different sets, and we got to 165. Actually, I didn't get to 165. I actually bungled it. And because this is a slightly complicated method, it's easier to bungle. Our friend Rob came up with a better method, a clearer method. So he said, well, we break the 4 tumblers into 2 groups of 2. So we've got the 2 at the front and the 2 at the back. As a whole, those numbers need to add up to 8. So the numbers could be, the number accounted for by the first 2 could be 0, and then the last 2 would have to be 8. Or the first 2 could add up to 1, and then the last 2 would add to 7. The first 2 could add up to 2, and then the last 2 to 6, and so on. These are the options. Now, let's say they add up to 3 and 5. There are 4 ways of making 3 with 2 tumblers. You can go 3, 1. No. To make 3, you go 3, 0, 2, 1, 1, 2, 0, 3. There are 4 ways. There are 6 ways of making 5. 0, 5, 1, 4, 2, 3, 3, 2, 4, 1, 5, 0. So what Rob did was, for each of these different options, work out the different ways you could make them up. So you basically get, and it's quite pretty, there's an obvious pattern here: 1 times 9, 2 times 8, 3 times 7, 4 times 6, down to 9 times 1. Then all you got to do is just crunch that out. So it's 9 plus 16 plus 21 plus 24 plus 25. Rob also noticed a symmetry here. So the first 1, 2, 3, 4 numbers add up to 70, and they're the same as the last 4 numbers. So it's 70 plus 25 in the middle makes 165. So now I've got the answer 2 ways. There's a third way, which kind of I thought about while I was brushing my teeth that night, which is, well, we could just list them. Just list them in numerical order. And certainly when I was at school, I would have done this. And with 165, it's definitely possible. I mean, with 1,000, I'd think twice, although you might be able to have a go. With 10,000, it's a bit too many. But with 1,000, I think you definitely have a go. And what this tells you, actually, is that this isn't a great combination lock. Because if a human has time to try all the options, then the combination lock is fundamentally breakable. So really, only when you get to about 10,000 does it get, I would say, to get to be a really decent lock. It took me about half an hour or something just to chug these out while I was listening to music. It's not particularly difficult. But listing them is interesting because patterns start to jump out. So firstly, what I noticed is that there's a lot that start with 0. So when we count them, there's 10 in a row. So there's 10, 20, 30, 40, and another 5. There's 45 starting with 0, but then there's fewer starting with 1, fewer starting with 2. Actually, there's only 3 starting with 7. There are 6 starting with 6, and only 1 starting with 8. So as the front number rises, you have less to go around, less to spread over the later tumblers, and so you have fewer options. So I just wrote these down. So starting with 0 we have 45, starting with 1 we have 36, with 2 we have 28, and so on. I just wrote these down, and it struck me these are the triangular numbers. So the triangular numbers, 1 plus 2 is 3, 1 plus 2 plus 3 is 6, 1 plus 2 plus 3 plus 4 is 10. These are the triangular numbers, and they're exactly the same as these. So why is this? What's going on? And then at about 11 o'clock at night, it all started to fall into place, really, which is, there is another approach to this, which is, let's start by just imagining we just had 2 tumblers on the lock. If we want to add up to 8, there are 9 options. There's 9 ways of doing that. If we had 3 tumblers, then if the first tumbler is 0, there are then 9 options for getting 8 in the second and third together. If the first tumbler is 1, there are 8 options for the rest, because they have to add up to 7. If the first tumbler is 2, there are 7 options for the other 2, because they have to add up to 6. So if there are 3 tumblers, there are 9 plus 8 plus 7 plus 6 plus 5 plus 4 plus 1 is 45 options. Okay, that's for 3. What if we have 4? Well, if we have 4 and the first is 0, then we're just back to 3 that have to add to 8. So there's 45 ways of doing that. If there are 4 and the first one is 1, then we then need the next 3 to add up to 7. And in this case, we can see there's 36 ways of having 3 tumblers add up to 7. And then if the first is 2, the last 3 have to add up to 6, and there are 28 ways of doing that, and so on. So for 4 tumblers, overall, there are 45 plus 36 plus 28 plus 21. Each of these different options corresponds to a different value in the first of the 4 tumblers. And if we add those up, we get to 165. This opens up the prospect of generalization. So this allows us to think about generalizing to other situations. And this is very exciting in mathematics. It's a great thing to do. So our answer was the sum of the first 9 triangular numbers. But if we wanted the tumblers to add up to 7, we realized that actually that would be the first 8 triangular numbers. The number of ways of doing that, we need to add the first 8 triangular numbers, which is 120 ways. If we want them to add to 6, we'd need the sum of the first 7 triangular numbers, which is 84. So all of a sudden, we found a way not just to work it out for 8, but also for 7, 6, 5, 4, 3, 2, 1, and so on. What if we want them to add to 15? Well, this becomes a bit more complicated because there are 9 ways of getting 8 with 2 tumblers. There are 8 ways of getting 7, but how many ways are there of getting 15? There are not 16 ways. There are actually just 4 ways. So 6, 9, 7, 8, 8, 7, 9, 6. So when you get bigger numbers, you end up with fewer ways of getting the number. I mean, for instance, if there's get to 18, there's just 1 way. So there are 4 ways of getting 15, which is actually exactly the same number of ways of getting 3. 18 is 3 is 18 minus 15, so there's kind of a mirroring or a duality going on there. So basically our method is breaking down for sums that go over 9. So it works for 9 because there are 10 ways of getting 9, but it doesn't work for 10 because there's only 9 ways of getting 10. What if we had 5 tumblers? So we can do this. We can do it with 5 tumblers. So with 2 tumblers, the number of codes is n plus 1, where we're looking for the codes to add up to n. With 3, it's the n plus 1th triangular number. With 4, it's the sum of the first n plus 1 triangular numbers. And with 5, it's the sum of the sums. It's the sum of the first n plus 1 sums of triangular numbers, and so on. So with 6, it would be the sum of the sums, and so on. So this gives us a way of generalizing to any number of tumblers. We also have a way of actually generating a formula, what I'd call a closed formula for the result. And actually Bill asked in his email, is there a formula? Because the point is, if we want the tumblers to add up to n, less than or equal to 9, then the answer is the sum of the first n plus 1 triangular numbers. So the first n plus 1 triangular numbers look like this: 1, and then 3, and then it'll be 6, and then it'll be 10, 15, and so on, up to n plus 1, n plus 2 over 2. So when n is 8, so we're looking for codes that add to 8, we end up with 90, because it's 9 times 10 over 2, 45. And actually, also, we can work out a formula for the sum of the first n plus 1 triangular numbers. That formula is n plus 1 times n plus 2 times n plus 3 over 6. So if we pop 8 in, we get 9 times 10 times 11 over 6. If we work this out, we can cancel. So cancel a 3 from the 6 into the 9, we end up with a 3 there. And then cancel a 2 into the 10, we get a 5. So it's 3 times 5 times 11 is 165. Hooray! So we've actually got our solution a different way. Let's be brave. I've not prepared this earlier. Let's put in 7. So if we put in 7, we get 8 times 9 times 10. So 8 times 9 is 72, times 10 is 720. We divide by 6, we get back to 120, which is, I believe, we said 120, didn't we, for 7. So this formula works. It's really nice. So works for n equals 8. It works here. So what I find interesting is, what is mathematical research like? Well, firstly, it's social. It's something that people do together. It's emotional. In other words, I was frustrated when my answer was a bit clunky and didn't really work, and Rob's was much smoother. I was like, why didn't I think of that? We borrow ideas for each other, giving each other credit, of course. We stay up late to get to the bottom of things, so it was 1:30 in the morning by the time I'd actually got to the bottom of this, and I just collapsed in a heap after sending an email. We do maths like science, so what's interesting is we can generate data sets, like we can generate this set of numbers, and then we can do science on the numbers. So we can look for patterns in the numbers. Same way as if you're looking for patterns in bird populations, or maybe, an atomic structure. We can see that there's a pattern here, and then we can try to work out what is the rule that's governing the pattern. Why is that pattern occurring? So we can sort of do science on the mathematical stuff we grind out. We're not happy with one solution, so actually in this video I think we've looked at 4 ways of solving this problem, and that's really interesting because maybe new ways of getting the result will produce a new level of understanding. We try to generalize, so we solve this problem, but we try to see if the methods that we find can allow us to solve a larger, more general set of problems. And also there might be mistakes in it, and we don't want mistakes. We get upset when we make mistakes. But there might be mistakes, and sometimes those mistakes trigger us to new and deeper understanding. So if you find any mistakes, please do let me know. This is the 3rd version of the video. The first 2 had mistakes in. This may have mistakes in too. And if you find them, please tell us in the comments. I hope you've enjoyed this. If you have, please hit like and subscribe to see more in the future. We are now going to take this ham. We're going to wave it. He's straight here. The dog is straight here. We're going to wave it around in front of the dog and see if he wants some. This is a scientific experiment. Do dogs enjoy ham? I think it's a simple yes. I hope you've enjoyed this. We've enjoyed this, and we really look forward to seeing you next time. Don't we, Chewy?